Hello everyone, this is Dr. Young, and in this video we're going to talk about two more electrophilic aromatic substitution reactions, nitration and sulfonation. So I've got here three listed, right? Nitration, sulfonation, and desulfonation. I'm just going to show you the reagents really quick so that you know that this plus this makes that. For nitration, you're always going to see nitric acid, right? We've got the nitro group. So here's our nitro group, hence the nitration. And this nitro group, if I draw it out here, the nitro group is an N double bonded to an O and single bonded to another O, but that O has a negative and this N now has 4 bonds instead of 3, so it's positive. So overall, it's a neutral group. So we just write NO2, we don't write any charges on it. But the nitro group looks like that. And I've shown you in previous videos, right, that a nitro group is a very strong deactivator. It's positive at that point of attachment on the ring, and it's got a pi bond, so it can pull electrons out by electron delocalization with resonance, right? As far as the reagents that you're going to see here is you're always going to see nitric acid. It's where the nitrogen comes from. And then there's usually some other acid around, so like sulfuric acid, and that'll be the one that I use the most. That's probably going to be the one that you see. So you're always going to see nitric acid, which is the main component, and then sulfuric acid, just because we need another acid source, and I'll show you why on the next slide. Then we have sulfonation. Sulfonation here, right? So here's your sulfonic acid. Your sulfonic acid group, that looks like this. All right, so I've got my aromatic ring, a sulfur that's double bonded to an O, double bonded to an O, and then has an OH on it. So here's your sulfonic acid. And these are very strong acids. Strong acid. It's very easy for that hydrogen and that sulfonic acid to pop off. It's got a negative pKa. But that's what it looks like, and again, we just write SO3H, or we can draw it out with the sulfur double bonded to those two O's, and I'll show you the mechanism of how that's formed also. As far as the reagents for the sulfonation go, you will always see sulfuric acid, H2SO4, so that is actually something that you're going to see in common with nitration. But with sulfonation, you're not going to see any nitric acid. So you're either going to see just concentrated sulfuric acid, you might even see concentrated afterwards. What you also might see is you might see SO3 written somewhere. This sulfur trioxide might be written somewhere also to either emphasize that that's the electrophile that's being added, or people can try to bubble through the sulfur trioxide also. I usually show the SO3 also for my students. And then this last reaction is just the reverse, right? So it's the desulfonation. So I can actually take that sulfonic acid and remove it, right? I can take it off entirely. And the way that we do that is we simply add acid and water and we heat it up. And that's going to remove the sulfonic acid. Now, why would we do that? We're going to talk a little bit more about synthesis reactions with these benzene ring derivatives. But what we're going to do is we're going to use it as a protecting group. Right, the idea is that we can use the sulfonic acid as a protecting group and then remove it later, kind of like we used an acetal to protect a carbonyl and then remove it, or we could protect an alcohol by turning it into an ether and then removing it. It's going to be the same thing. So can act as a protecting group. That's how this is going to work, and we're going to use it to block mostly the para position, but we'll talk more about orthometapara later. So here's kind of the three reactions. These kind of go together. So let me show you the mechanism of nitration. So I'm going to draw out my nitric acid and my sulfuric acid. I'm just going to take my sulfuric acid and split it up. H plus, HSO4 minus, it's a strong acid, so is nitric acid. But we're in extremely acidic conditions is the idea here. Really super low pHs. So I'm going to draw out my nitric acid. Minus O, and then there's a positive on the end. Now, we have a lot of acid around. I'm going to go with the mechanism that's in the book, although I think it's suspect, just because it's a little bit shorter, and I am not going to ask you to draw the mechanism for how these super electrophiles are formed. I'm just showing you so that you can kind of see them. What happens overall-ish is eventually, and I'm kind of cutting some corners for this mechanism, so excuse this part. Eventually, you're going to get what's the equivalent of water on one of these oxygens. And I'm being kind of, hesitant about this because really it should be this O out here that picks up that hydrogen, but we're just going to go with it. Because what happens is that you lose the equivalent of water from this nitric acid. And that's how you form your electrophile, right? So now I have water, I just kicked water out. And then I have my super electrophile, so that N is now double bonded to two O's and is positive. This is your quote unquote NO2 plus. And again, the idea here is that this is very electrophilic, right? So here's how we made that super electrophile for our electrophilic aromatic substitution. Right, and it's very electrophilic because it's got a positive charge, a full-on positive charge there. And then from here on out, the mechanism is just the same old electrophilic aromatic substitution, right? Your benzene ring is going to go get whatever the electrophile is. In this case, it's the nitrogen, right? Because that's the positive. Nitrogen can't have 5 bonds, so one of these bonds breaks. Sorry, I should have drawn my lone pairs on these oxygens here. 1, 2, 3, 4, 5, 6, 7, 8. Which means, so we've added the thing, right? This is that addition step. And I'll put a hydrogen here, positive here. And then we had all those resonance structures. I don't really want to show them right now just because I don't want to. It's just kind of, it's the same 3, right? I'd move this over here and then that over there to draw my other resonance structures. But we know that the last step, right, is that this H pops off to give us our aromatic ring back. But in doing so, I have made my nitro group, right? I have my nitro group attached here. And I've got a little bit of H plus that forms, but that's fine. We're already in acid, right? So that is this. So it's the same mechanism, right? Remember the electrophilic aromatic substitution mechanism is just your benzene ring goes and gets the electrophile. You have a resonance stabilized carbocation, and then you do an E1 type of elimination, right? Just a hydrogen leaves, you form a double bond again, you regain your aromaticity, and you're done. That's really it. Now, sulfonation is going to be very, very similar. And sulfonation, though, I'm adding the sulfur trioxide, that is the electrophile. And one of the reasons, I should just put this as an aside here, one of the reasons why sometimes you can see just H2SO4 written, if it's really concentrated, is that H2SO4 is in equilibrium with sulfur trioxide and water. Right? If you add those up, if you combine them, that's the same number of sulfurs, oxygens, and hydrogens on either side. So when you hydrate sulfur trioxide, you get sulfuric acid. And as a side note, this is one of the things that can happen if you're burning sulfur-containing compounds and you're going to get acid rain. If you're burning something and you make sulfur trioxide up in the atmosphere, it combines with water, makes sulfuric acid, and then when it rains, then it's kills forests and lowers the pH of rivers and lakes and stuff like that and kills stuff. But anyways, I was mentioning that because again, you might not see sulfur trioxide written out explicitly. If you ever see just H2SO4 or H2SO4 concentrated or like 85% or something that makes it sound like there's a lot of it, that is saying that there is SO3 around, right? Because again, it's in equilibrium with each other. And so for this one, it's if I have SO3, then I can just skip some steps here, right? This is our super electrophile because you've got 3 very electronegative oxygens on here. So this sulfur is very positive. And it's got the pi bonds on it, so it can accept electrons really easily. So I can just attack the sulfur. One of these kicks out. One of these kicks out. So that's the first step of my electrophilic aromatic substitution. So now I've got S, double bond O, and O minus. And I've got an H. And now my positive charge. I will draw the resonance structures for these because I feel bad I didn't do it for you last time. Right, I can have one pi electron, one pi bond move over to that carbocation, leaving my positive charge there. I can do the same thing, moving it over one more place, just spending all this time drawing lone pairs. And the H. I can have it drop one more. So I get these 3 resonance structures. All right, I broke the aromaticity. Like we said, in all of them, the last step is that the H is removed or falls off to give us our product. So now I've regained my aromaticity by doing that elimination. I've got some H+, and now I've got my sulfonic acid. And since I'm in such acidic conditions, probably what happens is that hydrogen ends up on the O so that you get your sulfonic acid. So that's your mechanism for this one. Again, pretty straightforward because the electrophilic aromatic substitution mechanism is the same for all of these. It's just how do we generate that really good electrophile. So let's look at a couple of examples. So here's just 3, right? And again, these are going to get more complicated once we know all of the electrophilic aromatic substitution reactions. And then we'll start doing some like, well, what if there's already something on there? How do things direct? Are they going to go ortho, meta, or para to one another? But right now, we're just going to kind of keep it simple. So I just want you to be able to recognize, right, when you see, right, sulfuric acid, and that's all that there is, and this is concentrated, right, conc is concentrated, that you should be drawing something with the sulfonic acid, SO3H. That's all you got to draw. If you need to suddenly put a nitro group on there, what I want to see is that you write that, oh, I need nitric acid and I need sulfuric acid. That's how I'm going to get that nitro group on there. I'm going to do a nitration. And then lastly, the other thing for you to remember is that when you see, oh, I should have written heat here. Sorry. Let me do this. Comma, heat. You got to heat this up. If you see this, and that's the only reagent that you have, and you have an aromatic ring with a bunch of stuff on it, remember that removes this, right? That's going to take this sulfonic acid off. So you just redraw your product exactly. Nothing else is going to be removed by that, but just now without that SO3H. So you can remove that. So practice those, do some practice problems. Watch the next video, which is going to be on the Friedel-Crafts alkylation and acylation, which are our last 2 electrophilic aromatic substitution reactions. So study up, watch the next video. Good luck.